Hello everyone. This is a screencast for my final year project. My name is Costanza Improta and my supervisor is Ting Ting Mu. The aim of this project is to generate a concise and coherent descriptive paragraph of an image with the aid of a descaptioning approach. Image captioning can be defined as the process of automatically generating textual descriptions of an image. It consists of interpreting the features of an image, or its pixel information, and translating them into natural language. However, the majority of the state-of-the-art models output a single sentence of around 20 words, which is hardly enough to describe the main observation of the image, let alone condensing the entirety of its visual content. Compared to sentence-level captions, paragraphs are longer, more informative, and more linguistically complex. A richer and longer caption, describing the image in a cohesive and coherent way, would not only provide support to the visually impaired, but it would also enable real-time captioning and summarizing techniques. For these reasons, this project focuses on paragraph generation. The best results on image captioning are currently achieved by neural network-based methods, which use neural networks for both image text embedding and sentence generation. These methods are based on the encoder-decoder pipeline, consisting of a convolutional neural network, or CNN, which learns directly from the image data through patterns, and a recurrent neural network, or RNN, whose decisions are made by considering both the current input and the previous outputs. First, the CNN encodes the image into its vector representation, and then the RNN acts as a language model to generate meaningful sentences describing the visual content in detail. The model presented in this work is based on long short-term memory networks, or LSTMs, which are a specialized type of RNNs. A long short-term memory network takes three inputs: the input of the current time step, the output from the previous LSTM unit, and the memory of the previous unit. The advantage of LSTMs over traditional RNNs is that they retain information for long periods of time, allowing for important information learned early in the sequence to have a larger impact on model decisions made at the end of the sequence. The model presented in this work is made of a region detector, which extracts the features of the most salient regions of an image, a region pooling step, where the feature vectors of the regions are then pooled into a single vector, and a stack of LSTMs, otherwise called a hierarchical neural network, or HRNN, to reason about the language and to translate the features of the image into natural language. A publicly available dense captioning model is used as a region detector. It is capable of localizing and describing a maximum of 50 bounding boxes per image, each of which encloses interesting information. Despite its ability to capture interactions between entities present in the scene and then translate them into words, the dense captioning model may return several overlapping bounding boxes, which are then captured in a similar way, resulting in redundancy. The feature vectors describing these possibly redundant 50 regions are then pooled and input to the HRNN. There, a sentence LSTM identifies a maximum of 6 topics to be tackled in the paragraph, 1 topic per sentence, and feeds each topic vector to a copy of a word RNN, which populates the sentences with exact words. Finally, all the sentences output from the various word RNNs are formatted and concatenated together to produce the paragraph for the given image. This model was trained on the visual genome dataset, investigating 3 different bias vectors, and it was later saved at different number of epochs. The first bias vector tested is called bias, and it is the word frequency in the ground truth. The second bias vector tested is called normalized bias, and it is the previous one but normalized. The third and final bias vector is called no bias, and it is a vector of zeros. In the experiments to follow, the best two trained models per bias vector type are taken into consideration. This is a random image from the training dataset, along with the relative ground truth paragraph. Here it is shown how this image is captioned by the 6 models mentioned beforehand. Comparing the generated captions to the ground truth, it can be stated that the majority of the ideas present in the ground truth were also conveyed in the paragraphs. In the example shown here instead, a random image from the validation dataset is captioned by the 2 best performing models for each bias vector type, as mentioned before. The results are far from perfect, but they are still pertinent. Despite the project being fully runnable for terminal commands in Python, a graphical user interface was developed to facilitate the user experience and give easy access to the tools to users unfamiliar with Python. For the GUI, the user can load different pre-trained models and test on the go a given image. The user is able to refer to the original image while reading the produced paragraph and eventually compare it to the ground truth if the chosen image is part of the training dataset. The user is also able to visualize the graphs of loss for the currently selected model, and this allows him to make an informed decision when it comes to choose the pre-trained model to load. Being this one of the very first models for automatic paragraph generation to describe an image, objective evaluation methods on such a subjective topic are a current area of research. For this reason, the network was objectively evaluated with a good combination of language metric scores, lexical analysis, and human evaluation. One of the linguistic metrics used to compare the produced paragraphs with the ground truth is the cosine similarity. The closer the output value to 1, the higher the similarity between the 2 paragraphs. Therefore, based on the results shown, there is a very good similarity between the paragraphs produced and the ground truth. To analyze the paragraphs from a syntactic point of view, a series of lexical analysis evaluations were performed. In particular, lexical diversity, which reflects the range of different words used in the text. The closer the value to 1, the higher the diversity in the generated words. The results show a great variety of words used in the paragraph on average. Therefore, diverse topics are tackled in it, and redundancy is avoided. Additionally, between 2% and 4% of the words in a paragraph were classified as pronouns, showing that in some cases the model is applying coreference. Finally, to evaluate the pertinence of the descriptions produced for a given image, a Google form containing random images from the training and validation datasets was set up. People ranked each caption from 1, being totally unrelated to image, to 5, being totally related to image. Here, no particular model resulted to be the clear preferred one. Therefore, despite the model being very good from a theoretical point of view, the results of the form show that it is yet to reach a language reasoning comparable to human level, also due to the lack of sentences with a perfect grammar. This could be solved with an additional natural language processing model, which ensures the grammaticality of the sentences. Thank you for watching.